3. Central limit theorem and sampling distributions. We start from the sampling distribution. Let's say we have a distribution of heights of all basketball players of North America by their heights. This distribution is close to the normal probability density function with the mean of 6 feet and some standard deviation sigma. We can consider different samples of 10 players. Each sample has its average height. As a result, we have a big set of these averages. The distribution of these averages is called a sample distribution. We will illustrate that the mean of this distribution is equal to the mean of the original distribution, and the standard deviation is less than the standard deviation of the original distribution by coefficient of square root of 10. We will do that with the help of numeric experiment using Book 4 or Collab 4. See the links in the description of the video. In our program, we have a random number generator. It generates random numbers uniformly distributed from 0 to 1. We divide this interval into 100 bins, from 0 to 0.01, from 0.01 to 0.02, and so on. Each generated number falls in one of these 100 bins. Let us run the generator 100,000 times. As a result, about 1,000 generated numbers fall between 0 and 0.01. About another 1,000 numbers fall between 0.01 and 0.02, and so on. The distribution drawn at the slide is normalized, divided by 1,000, to make the blue area equal to 1. We see the result which we expected to see. This is approximately uniform distribution. Now we will take samples. Instead of 100,000 numbers, we take 100,000 samples of some size. Each of these samples has an average value. We have 100,000 averages. How these averages are distributed? Is it still the uniform distribution? Let us start from size equal to. We have 100,000 random pairs. To see their distribution, run the program. We see that the distribution is not uniform anymore. It has a triangle shape. The area is equal to 1. The average of the averages is 0.5. The standard deviation of the averages is less than the standard deviation of the original distribution. Why for size 2 we have a triangle distribution? Let's understand it on the example of rolling 2 dice. There are 36 possible outcomes. The sum of 2 dices can be from 2 to 12. The outcomes of some 2 and some 12 have the minimum probability, 1 over 36 each. The outcome of some 7 has the maximum probability, 6 over 36. It explains why the sum of 2 trials has the triangle frequency distribution. Now try 100,000 samples of size 3. We see that the average of the averages is still close to the mean of the original distribution, but the shape of the distribution becomes similar to the bell shape. And the width of this shape decreases. Most of the numbers are between 0.3 and 0.7. Finally, run the cell with 100,000 samples of size 30. We see that while the size of the samples increases, the mean of the new distribution stays equal to the mean of the original distribution. The shape becomes closer to the shape of the normal distribution, and the width becomes narrower and narrow. We can check that the product of the standard deviation of the new distribution and the square root of the sample size approaches to the standard deviation of the original distribution, which is 0.29. It is interesting that if we started not with the uniform distribution, but with any other distribution, by replacing the random number generator, we would have the same result, which is called the central limit theorem. Denote the sample's average as x bar, the mean of the standard deviation of the original population as mu, and the standard deviation as sigma. Then the central limit theorem can be formulated as follows. Statistics z equal to x bar minus mu over sigma over the square root of n has a standardized normal distribution.